Hello, and welcome to the third introductory lecture. And this is intended as introducing the fundamentals of solid state physics to undergraduates that have had some sort of freshman level modern physics course, but have not yet had a solid state course. So this lecture is about electrons. And there are going to be a number of topics covered, some of them very briefly. So we will start with a free electron gas, which is a very simple model for electrons in a metal. A related topic that we'll discuss is density of states. Then we will move on to some electronic parameters that can be extracted if we have a little bit of information about electrons, energy versus momentum relations. And this includes velocity and effective mass. Then I'll have a little bit of discussion about sort of the differences between metals, insulators, and semiconductors. And then, all right, up until I guess the third topic written here, the lattice is not in the picture. So we're only talking about electrons. So at around this point, I'm going to introduce the lattice back in. And this allows us to have sort of a more realistic picture of electrons in a material because a real crystalline solid, it has the atomic lattice that was discussed in prior mini lectures, and then it also has the electrons. And then finally, the last topic is going to be a little bit disjointed from the others, and it is the tight binding model, which is a method of calculating energy versus momentum relations for electrons in a crystalline solid that takes the opposite approach of everything written above it, where the opposite approach is sort of completely delocalized electrons as a starting point. The tight binding model is the opposite approach, so localized electrons as a starting point. Okay, so let's get into it. The first topic is a free electron gas in 3 dimensions. And in a solid state class, this might be introduced first in 1 dimension and then move into 3, which captures more realistic materials. But we'll just start with 3 dimensions here. So as I mentioned, this is a toy problem, but it turns out to be applicable to many simple metals, such as sodium or copper and other metals on the same column of the periodic table. And what this is it's basically an infinite potential well. So that's how we model a metal. We model it as an infinite potential well or particle in a box. And in contrast to sort of the original formulation of particle in a box in a quantum mechanics class, this particle in a box has many particles in it. Okay, so this model makes the following assumptions. So one assumption is that the valence electrons are completely delocalized over the entire solid. So this statement sort of implies a metal, but actually the same formalism is used to produce insulators and semiconductors. But in any case, we start off with the assumption that valence electrons are completely delocalized over the entire solid. There might be some core electrons that are still stuck to their host atom, but the valence electrons, once they've been given up, they're completely delocalized. And delocalized is sort of a fancy word to say that we're going to be treating these electrons as waves rather than particles. Okay, so that is one assumption. Another assumption that is just a temporary assumption is that the lattice is absent for now. And then the last assumption is that electrons do not interact with one another except for Pauli exclusion. So this is modeling a real crystalline solid minus the lattice. And there are going to be many electrons involved. And normally electrons do experience Coulomb repulsion with one another. However, we're ignoring all that and we're saying the electrons do not interact with each other except for Pauli exclusion. All right. Um, so, um, so this last statement is also the reason that this model is called a free electron gas. So in this context, a gas does not mean that the electrons are zipping around in free space. They are considered to be electrons in a metal. However, the word gas in this context means that they interact with each other not at all or very, very weakly, analogous to how atoms in an ideal gas or even a real gas interact minimally with one another. Okay, so um, uh, so these are our assumptions. So let's go back to the model of an infinite potential well or particle in a box from quantum mechanics class. So in that model, you have particles that are confined to a specific region in space. And inside that region of space, they are not subjected to any forces. So the potential energy term in the Hamiltonian is zero. And the Schrodinger equation just ends up being the following. It ends up being that for free particles, and then when you apply boundary conditions, that's where you introduce the fact that the electrons are actually defined. So let me write down the Schrodinger equation for free particles in three dimensions. So negative h bar squared divided by 2m times a second derivative with respect to x plus second derivative with respect to y plus second derivative with respect to z. And these derivatives act on the wave function, which is going to be labeled by k. I'll explain what k is in a little bit. And this is equal to the energy, where the energy solutions are also labeled by k, multiplying the same wave function. All right, and as a reminder, the r in the parentheses here is sort of a coordinate that represents x, y, z. Okay, so, all right. So one solution to this form of the Schrodinger equation is a plane wave. So this can be written as psi sub k r is equal to e to the I k dot r, which if we want to write it very explicitly in Cartesian coordinates, this is equal to e to the I kx times x plus ky times y plus kz times z. All right, so that is a wave function that turns out does solve this differential equation right here. It is a solution to the Schrodinger equation. And let me go ahead and plug it in at this point. And when we plug it in, we get the following. We get h bar squared divided by 2m. The negative has dropped out because you're taking two derivatives with regards to each variable, and there's an I up in the exponent, so you get a negative sign from I times I. So h bar squared divided by 2m times kx squared plus ky squared plus kz squared, whoops, supposed to be squared, is equal to the energy solutions that are labeled by k. And we can define this parameter, kx squared plus ky squared plus kz squared, by sort of some radial distance k from an origin. let's call this k squared. So then the energy as a function of, of k is equal to h bar squared, k squared divided by 2m. So as a reminder, K is it can be called either a wave number or a quantum mechanical momentum. So if you think of it as a wave number, it is essentially encoding, if you consider its magnitude, it is encoding information about the wavelength, but it does this in an inverse manner, so it's equal to 2 pi over lambda. It is a vector quantity, so it's also encoding information about what direction the wave is moving in. And if you think of it in terms of quantum mechanical momentum, then uh, momentum is equal to h bar times k. So, uh, so in the context of solid state physics, if you see a k, usually you call it momentum. Okay, so that is the wave function and the energies that we get. And now we apply boundary conditions. So boundary conditions are where we actually specifically use the fact that our model is an infinite potential well. And the specific form of the boundary conditions that I'm going to write down is maybe a little bit different than what you've seen in a modern physics or quantum mechanics class. And they are actually going to be periodic boundary conditions. So I'm going to write it down for the x direction, and I'm not going to write it down for other directions. So the periodic boundary condition for the wave function is that psi of x plus L, y, and z is equal to psi of x, y, z. And this is going to be true for y, and it's going to be true for z. I'm not going to write it down. Okay, so the periodic boundary conditions do two things. First of all, they capture the fact that a crystalline solid is essentially infinite. That is to say that the physical size of the crystalline solid, which is L, is so much larger than the spacing between adjacent atoms, which we traditionally call A, that it is effectively infinite. And this is something that is captured with periodic boundary conditions, where you really do get an infinite solid by mapping every boundary onto the opposite boundary. Another convenient thing about periodic boundary conditions is that you don't end up with a preferred direction, which is which correctly captures what is happening in crystalline solids. Okay, so let's apply this boundary condition to our wave function. So let's go ahead and plug it back in. And I'm just going to plug in this one that I actually wrote down. So e to the I kx times x plus L plus ky times y plus kz times z is equal to e to the I kx times x plus ky times y plus kz times z. All right, so then we just cancel out common terms, and we get that e to the I kx times L is equal to 1. And this equation is only going to be true if kx times L is equal to 2 pi times some integer n. So putting this all together, we get that permissible values of kx are 0 plus minus 2 pi over L plus minus 4 pi over L, and so on and so forth. And same situation for ky, and same situation for kz. Okay, so our boundary conditions have picked out selected or quantized values of kx, ky, and kz that electrons can take on, given the fact that they're confined to be inside this solid of length L in all dimensions. Okay, so so we have our solutions to a quantum mechanics problem. So the solution is applicable to nominally one particle. So we've the version of the Schrodinger equation that I wrote down a little bit earlier. Sorry, um, my other device lost its internet or something. So let me share my screen again. All right, so that's while that's going back up, I'll remind you that the version of the Schrodinger equation that was solved was only for one particle, and now we are going to make the guess that maybe it can work for many particles, and it turns out that this is an okay guess. All right, so what we're going to do now is we're going to put n electrons into these available states. And as a reminder, this is supposed to be modeling a real material. So N is the number of electrons, and it is on the order of 10 to the 23. So we're putting many electrons into these available states. So there are going to be certain rules and certain assumptions. So let me first write down the assumption. And the assumption is that the presence of many electrons does not affect the solutions to the Schrodinger equation. So let's say single particle solution still applicable for many particles. So this is an assumption. Okay. And then everything that I'm going to write after that is a set of rules. All right. So the first rule is that every state is defined by a unique quantized value of kx, ky, and kz, a unique coordinate. All right. So as a reminder, what we just derived above is with the periodic boundary conditions, there are certain selected values of kx, ky, and kz that are permissible, and every unique coordinate, kx, ky, and kz, defines a different state. It defines a different quantum mechanical solution. Okay, so after that, each state can only hold two electrons, one spin up, one spin down. All right, and this is where the rule that incorporates Pauli exclusion. So electrons are fermions, and fermions are subjected to Pauli exclusion, which is basically that they need to all be in different states, where the state it also incorporates information about spin. So if you have them in the same momentum state, in the same kx, ky, and kz, those two electrons better have one spin up and one spin down. And since there are only two spin states available to spin one half particle, that is the totality of how many electrons you can put in each momentum state. Okay, and then the last rule is that we fill low energy states first. All right. So this statement, first of all, this rule exists because what we're trying to calculate is sort of ground state properties at this point. And you get the ground state by sort of getting the lowest possible energy for all of the electrons together, and you can only do that if you if you fill the lowest energy states and then the next lowest, the next lowest, the next lowest until you've used up all your electrons. So anyway, so we're going to be filling up lowest energy states first. So I want you to notice that so every state is defined by a unique kx, ky, and kz. But you can have different values, different coordinates, kx, ky, and kz, that still correspond to the same energy because of this equation. So as long as kx squared plus ky squared plus kz squared is equal to the same value, which you can certainly have happen for different values of kx, ky, different coordinates rather of kx, ky, and kz, then the energy will be the same. So I want you to remember as I scroll down that the energy is going to be proportional to k squared, where k squared is equal to kx squared plus ky squared plus kz squared. Okay, so scrolling back down, this last rule, what it geometrically corresponds to is you have a sphere in k space. So the coordinate space where this sphere lives is kx, ky, and kz. And this sphere has some radius k, and along the surface of the sphere, it is all a single energy because the energy is proportional to k squared on the surface of a sphere of radius k. K squared always takes on the same value, so every sphere has the same energy. So when you're putting n electrons into the available states, the way you should think of it is filling up sort of spherical shells of constant energy, then moving on to the next spherical shell, the next spherical shell, the next spherical shell. Okay, so that is how we fill our available states with our n electrons. And when we have used up all our electrons, we fill to energy called the Fermi energy. And the Fermi energy is equal to h bar squared divided by 2m times the Fermi momentum squared. So the subscript F always stands for Fermi in the context of this of solid state physics. And let me just label this the Fermi energy. All right, so the Fermi energy is sort of the highest occupied energy level in the ground state. All right, so now we're going to calculate what the Fermi energy actually is in terms of materials parameters. Okay, so let's do this. So after we have filled up we've used up all of our n electrons, we have a sphere of radius kf in k space, and the volume of this sphere is equal to 4/3 pi kfq, because that's the equation for the volume of a sphere. So the electrons, they cannot take on any arbitrary coordinate, but rather they are confined to specific voxels that have a volume 2 pi divided by L cubed. And where does this number comes from? It comes from our quantization condition up here. So the permissible values of Kx differ from one another by 2 pi over L. And similarly, the permissible values of Ky differ from each other by 2 pi over L, and same for Kz. So the volume element that corresponds to a single state is equal to 2 pi over L cubed. Okay, so so this denominator is essentially the volume of each state. The numerator is the volume of this entire sphere. And the last ingredient is that each state can hold two electrons, one spin up, one spin down. So we have two multiplying this thing. All right. So that is an equation for the total number of electrons. So we have filled up this Fermi sphere in such a way that we sort of get the ground state configuration. We fill the lowest energy states first before moving on to the next one. So when we filled up to the Fermi energy, there are no states at lower energies that are empty. Okay, so we've used up all of our n electrons, and let me just simplify the equation on the left to get V times kF cubed divided by 3 pi squared. That is the quantity that's equal to n, and V is equal to L cubed, where L is the assumed length of our box of our metal on all three sides. So it turns out it doesn't matter what L is because most uh, physically measurable quantities are going to be um, are going to not are going to actually depend on electron density. And let me show this. Okay, so now I'm going to take this equation up here and I'm going to solve it for KF. So KF is just equal to 3 pi squared n divided by V to the power of 1/3. Okay, so this expression contains the number of electrons per volume. So the way it's written here, it implies the total number of electrons divided by the total volume of the solid. But it turns out that it doesn't matter, how big the solid is, because the electron density will be the same if you consider a solid of arbitrary size, and it'll be the same in that scenario as if you consider just one unit cell. So typically for a given material, you know what the unit cell is, and you know how many electrons each atom gives up, how many valence electrons are there. So the N over V that you have for one unit cell is applicable to the entire solid. So we don't need to know exactly what the volume is. We don't need to know exactly how many electrons there are in total because uh, um, many quantities will depend on just the electron density, which doesn't depend on how much material there is. Okay, so then the last step is to plug this back into the expression for the Fermi energy, and we get that the Fermi energy is equal to h bar squared divided by 2m times 3 pi squared n divided by v to the 2/3. Okay, so this is an expression for the Fermi energy, and the Fermi energy turns out to be a very important quantity in metals and also non-metals. So according to the derivation thus far, the Fermi energy is sort of, you can think of it as either the highest energy occupied state, or you can think of it as a boundary between occupied and unoccupied states. So if electrons in this Fermi gas want to make a low energy excitation, so a low energy excitation involves going from an occupied state where it's in to an unoccupied state where it's allowed to go. And at the Fermi energy, those excitations can be accomplished with very low energy. And it turns out that for real metals, it is the sort of properties near the Fermi energy that determine many sort of measurable or applicable quantities. So most transport experiments, so that's where you, for instance, apply a voltage and measure a current, those are pretty much determined by what's happening at the Fermi energy. Um, uh, Another thing, many of the thermal properties of materials depend exactly on the Fermi energy. Many ordering phenomena in materials, like if they become superconducting or they become charge density waves, that also is primarily driven by what is happening near the Fermi energy. So this boundary between occupied and unoccupied states is a very important parameter that we'll come back to many times. Okay, so the next topic that I want to cover very briefly is the density of states. And this is something that so for a free electron gas. It's something that can be calculated directly, um, and uh, and it is also a quantity that can pretty much be measured using scanning tunneling spectroscopy. So, okay. So the density of states, so in the context of this lecture, is going to be written as capital D as a function of energy. It's going to be defined as a derivative of the number with respect to energy. And usually I write the numerator here as d n twiddle with respect to energy, where n twiddle is the number of states as a function of energy. So I like to write it this way to distinguish it from just capital N, which is the total number of electrons. And basically, the idea is that for a free electron gas, or any collection of electrons, the number of states that exist at every energy is not necessarily going to be the same. It might be some function of energy, and this is what is captured in the density of states. Okay, so so let me show how we derive the density of states for a three-dimensional free electron gas. Um, and all right, so first we can write the number of electrons as a function of K. So in this exercise, what we're doing is we're filling up our sphere, our Fermi sphere in K space with electrons, but we don't necessarily need to fill up until we use up all of our electrons. So we just fill up part of the way and use some portion of our electrons, which I'll call n as a function of K. And this is equal to V k cubed divided by 3 pi squared. So basically, this is just the same equation as over here, except I am not assuming that the sphere has radius kf, because it doesn't. And I'm also not assuming that we use all n electrons, because we haven't. But other than that, that's where this equation comes from. And then what we can do is just plug in what is K as a function of energy. So energy is equal to it's equal to h bar squared K squared divided by 2m. And um, and then we just solve this for K, and we get that K is equal to square root of 2m times energy divided by h bar, and we plug in that into n. So we get n of E is equal to V divided by 3 pi squared times 2m times energy divided by h bar squared to the 3/2 power. And then we just take the derivative with respect to energy to get the density of states. So we get the density of states is equal to V squared divided by 2 divided by 2. That's supposed to be 3 pi squared, I think. 3 pi squared, let me correct my notes when I get back to it, times 2m divided by h bar squared to the 3/2. And then the one component that actually gets the derivative is the energy. So we get energy to the 1/2. All right, so basically for a free electron gas, the density of states as a function of energy looks something like this. So it goes quadratically, and then if we fill up to the Fermi energy, these are occupied states, and then for energies higher than the Fermi energy, those are unoccupied states. So this expression for the density of states is applicable for a free electron gas in 3 dimensions. If we were in 2 or 1 dimensions, there would be a different functional form. And if we did other things like introduce the lattice, which we'll do later, then the density of states will get a more complicated dependence on energy. But basically, what this indicates is that the density of states at the Fermi energy, which is where the density of states really matters, it gets larger as the Fermi energy gets larger. And how does the Fermi energy get larger? It gets larger if you have a higher electron density. So, for example, according to this, if you go from a monovalent to a divalent, so every atom gives up one or every atom gives up two electrons, then your Fermi energy will increase accordingly, and then your density of states at the Fermi energy will also increase accordingly, according to this formula. There will be some other considerations that will come in later. Okay, so everything that I've discussed thus far is at 0 temperature. So now I want to mention what temperature does. And what temperature does is it essentially introduces a Fermi-Dirac cutoff. So the Fermi-Dirac function is something you might have seen before, but it's equal to 1 divided by E to the energy minus mu divided by kBT plus 1. Okay, so I'm going to graph this function in a little bit, but first let me explain what mu is. So mu is what's called the chemical potential. The chemical potential is a thermodynamic quantity that relates to how many particles you have. So the chemical potential is approximately equal to the Fermi energy, at least for a 3 dimensional gas of electrons at any reasonable temperature. But the Fermi energy is strictly considered to be a 0 temperature quantity. So technically, when we're not at 0 temperature, we use the chemical potential in its stead. However, I should make it very clear, since this is sort of intended to be a more practical introductory lecture rather than purely academic, in sort of colloquial scientific speak. So when solid state physicists talk to one another, and even in the published literature, and I'll show examples in another introductory lecture about the ARPES technique. But in any case, it's very common to use the Fermi energy as sort of to mean the chemical potential. So the two terms are often used interchangeably, but they are technically a little bit different because the Fermi energy is only at 0 temperature. Okay, so let me graph this function by itself. So it's a pretty simple function, actually. So I'm going to have energy as the x-axis. I'm going to have this function as the y-axis, and then I'll have the chemical potential or the Fermi energy here in the middle. So 1, 1/2, and 0. Okay, so let me first graph what's happening at 0 temperature. So if you're at 0 temperature, this Fermi function is a perfect step function, okay? With the step occurring exactly at the Fermi energy. Now, if you are at higher temperatures, it looks very similar, except it's more of a rounded step function, where the width of the rounding is approximately 2 times kBT, or depending how much of the rounding you want to include in the estimation. But basically, at elevated temperature, the Fermi function, it's a rounded step function with the region where it strongly deviates from from an actual from its zero temperature quantity being of the order of 2 kBt or so around the chemical potential. And notably, at mu, it is equal to 1/2 exactly. At energy equals mu, it's equal to 1/2. And also notice that at energies that are very far from the chemical potential, it looks very much unchanged from what it's like at zero temperature. So the only changes really happen in the vicinity of the chemical potential or the Fermi energy, again, illustrating the importance of this specific energy regime. Let's see, what else did I want to say about the Fermi direct distribution? Okay, yeah, so what it physically represents is sort of an occupation probability. For example, if you are an electron at this energy, there is almost 100% probability that the state that you are in is occupied. Sorry, this might not have popped up on the other screen, but it'll get there. On the other hand, if you're considering a state that is at energy much higher than the Fermi energy or the chemical potential, there's almost 100% probability that it is unoccupied. And then it's only when you're in the regime of the chemical potential that you might have to actually calculate what is the occupation probability. Okay, and this concept relates to the density of states. For example, so here is sort of the density of states without considering temperature. And then I'm going to be plotting the density of states multiplied by the Fermi function. That is mostly going to be unchanged, except when you get in the vicinity of the chemical potential, then you are hit by this cutoff over here. So, so then this purple region is the states that are occupied at finite temperature. All righty. Okay, so let's see what's on the, okay, we're not there yet. Um, so, um, okay, the next topics that I want to discuss is connecting some of the formalism from the free electron gas to some measurable quantities about how electrons are moving in a material. Towards that end, let me, okay, so one topic, one measurable quantity, I should say, is electron velocity. All right, so electron velocity, this is something that we might want to know about electrons in a metal. How fast are they moving? So there are several ways to calculate them. Calculate this. So one that is the most widely applicable is the following. So it's in terms of a group velocity, which is equal to 1 divided by h bar times the derivative of the energy with respect to k. And as a reminder, for a free electron gas, energy is h bar squared, k squared over 2m. So if we apply this equation, we get that the velocity is equal to h bar k divided by m. So it will depend sort of which value of k you're talking about. So what are the kx, ky, kz coordinates of that electron? And then what radial k does that correspond to? That will tell you that electron's velocity. So that's one way of doing it. And this is the way that is very commonly used. So it turns out that energy versus k is something that is is measurable, and it's not always going to be quadratic. But even if it's not quadratic, this equation will still hold. So the tangent of the energy versus K curve at each value of K, no matter what its functional form is going to be proportional to the velocity of those electrons. So another way to get a velocity, and this velocity is so what we'll get using this way is going to be the same if you have a with the two methods. If you have a quadratic relationship between energy and K, if you do not, it's going to be a little bit different. So the other way of doing it is you write an equation that says momentum is equal to momentum. And we're going to write momentum in two different ways. So one way to write momentum is something that you have written in classical mechanics, just mass times velocity. And another way of writing momentum is something that is done in quantum mechanics class, h bar times k. And when you solve for velocity in this equation, you get the velocity is equal to h bar k divided by m. So this is another way of writing an electron's velocity. And if, as I mentioned, if the behavior is quadratic, you get the same thing either way. But there are scenarios, for example, where you get a group velocity that happens to be zero. So electrons, in some sense, behave like they're massless, I should say. They behave like they're massless, but if you calculate it this way, you do indeed uh, get uh, um, some velocity that factors into and also some effective mass, which we'll come to in a little bit. Okay, so um, yeah, so that is electron velocity, two ways to calculate it. So related quantity is the electron mass. Okay, so in a solid state context, electrons in many ways can behave differently from how they behave in free space. And one way that they can behave differently is that they can behave as if they have a different effective mass. So rather than just having a free electron mass, they might have what is called an effective mass. So this is usually in the literature called M star, sometimes M sub EFF for effective. And this effective mass can be written in the following way. So 1 divided by h bar squared times the second derivative of energy with respect to k. And starting from this equation, you can see that with one derivative of energy let me just take one derivative at a time. With one derivative of energy with respect to k, you get h bar squared k divided by m. That's what the first derivative is equal to. And then one more derivative gives you h bar squared divided by m. So that is where this expression comes from. So it should be noted that if you have a quadratic relationship between energy and K, if energy is proportional to K squared, then the effective mass that you derive will be the same for all values of K. So that's just this equation right here. However, you will not always have quadratic energy versus K, so the effective mass can itself be a function of momentum. Okay, and the last thing that I want to briefly mention before I move on to the next slide is electron-like versus hole-like bands. Okay, so all right, so electron-like versus hole-like bands. And this is another aspect of charge carriers inside a material. So they can behave differently from free space electrons in the sense of having a different mass. And another way that they can behave differently is some of them can behave like positrons. They can behave like positively charged particles, which are also called holes. And the way to distinguish that in energy versus K is essentially whether the energy versus K is curved upward or downward. Okay, so I'm going to draw two graphs of energy versus K. And just for kicks, I'll draw where the Fermi energy is. It's right here. So an electron-like band is this one, and a hole-like band is this one. So hole-like means sort of the carriers are effectively positively charged, and electron-like means that they are negative. So if you have electrons that live on a band like this, they will respond to electromagnetic fields as if they have positive charges. So given the derivation that we've had thus far with just a free electron gas, at this point, there's no way to get a hole-like energy versus K. However, when we introduce the lattice back in, there will be a way to do that. So with that, I will go ahead and introduce the lattice back in. And let's see. So all right, so that's going to be done here. However, I think I'll do a little bit of derivation before coming to this slide. Okay, so whoops, let me go back to the previous slide if I can. Looks like I'm, whoops, all right. Sorry about that delay. All right, just a moment for it to open up again. Mhm. All right, so it'll be popping up again. Okay, alrighty. So, okay, so thus far we have only discussed electrons, no lattice. And now we're going to turn the lattice back on. All right, so when we turn on the lattice potential, the following things happen. So first of all, okay, so let me, I'll draw it this way. Okay, so I'm gonna sketch out precisely what is on the slide that I gave a little preview of. However, it is, I'll do it step by step. Okay, so what I'm gonna be plotting here is the y-axis is energy, the x-axis is K. So if we just had a free electron gas, then I would just have a parabola. So E is equal to h bar squared times k squared divided by 2n. Okay, so this is everything that I've been discussing thus far. Okay, so when we turn on the lattice potential, the k-axis it becomes divided up into what are called Brillouin zones. So let me do that now. So all right. So basically, there's going to be some periodicity that's introduced. So there are going to be special values of k. So in one dimension, it's pi over a. So let me remind you that what I'm discussing now is for 1D, and I'm trying to draw these. Oh, whoops, let's not draw this here. All right, let's draw these 4 apart. So pi over A, 2 pi over A, 3 pi over A, 4 pi over A, and then minus pi over A, minus 2 pi over A, minus, oops, 3 pi over A, minus 4 pi over A, where A is the size of the unit cell. Okay, so between minus pi over A and pi over A, this is what is called the first Brillouin zone. And Brillouin zone is also called BZ. And the Brillouin zone is sort of uh, uh, it is related to the reciprocal lattice because if you notice, the width of this Brillouin zone is 2 pi over A. So then from pi over A to 2 pi over A, that is the second Brillouin zone, as is minus 2 pi over A to minus pi over A. So the second Brillouin zone is disjointed, and then the third one is also disjointed, and you sort of see the pattern. So this goes on until infinity. So this Brillouin zone structure of dividing up K space, this is essentially how the introduction of the lattice, so the periodicity of the lattice, how this is how it affects electrons. I haven't quite shown how it affects electrons, but our starting point is dividing up K into regions called Brillouin zones. So each of the Brillouin zones will have the same size. That statement is true in higher dimensions, although outside of one dimension, it is sometimes not trivial how you actually figure out what the higher Brillouin zones are. Okay, so the next, so let me draw some vertical lines here. Alrighty. So, we're introducing the lattice back in. So our free electron gas that we have from the discussion thus far, it needs to be invariant upon translations by a reciprocal lattice vector. So that is how the periodicity of the lattice really comes in. So what I can do then is I can translate this entire parabola by a reciprocal lattice vector by 2 pi over A. So let me go ahead and this is not going to go very well, but let me attempt to draw that. And I can also translate it by another 2 pi over A. So have another parabola starting here. And then I can also go in the other direction. I can translate it by a reciprocal lattice vector in the opposite direction. So have the parabola beginning at minus 2 pi over A. And same thing, translated by another reciprocal lattice vector and have it beginning at minus 4 pi over A. Okay, and I can continue this indefinitely. Okay, so the last thing that happens when we introduce the lattice back in is that there are gaps that open up when the bands cross. So for example, there will be a gap that opens up here and here and here and here. And this is going to be much clearer on the slide that I show coming up. So this opening of gaps is something that can be thought of in two different ways, at least. So one way to think about it is maybe more straightforward, and that is in terms of Pauli exclusion. So if you recall, every point on the energy versus K graph, it represents, or I should say every quantized value, every quantized permissible point on the energy versus K graph What it represents is it represents a state that can hold two electrons, one spin up and one spin down. So now, when you have them crossing, you have them intersecting, then you have a scenario where you are trying to put four electrons into one state, and that's just not going to fly. So opening up a gap can alleviate that. Another way that one can think about this happening is in terms of Bragg reflection. So in lecture two, I introduced the Bragg condition, which is that uh, 2k dotted with g is equal to g squared. So basically, if you have X-rays or neutrons or electrons, and in this case you have electrons, so you have electrons with some k, and that value of k dotted with a reciprocal lattice vector is equal to g squared. And if that equation holds, then you have Bragg reflection. So you have sort of that electron wave being reflected in the opposite direction. So in the one-dimensional case, this equation simplifies because we don't have to deal with vectors anymore. So in 1D, this simplifies to the values of k, where Bragg reflection occurs is equal to 1/2 of g, where g represents any reciprocal lattice vector. So in 1D, it's going to be 2 pi over a, or I should say plus minus 2 pi over a, plus minus 4 pi over a, and so on and so forth. So, oh, it equals actually 1/2 of plus minus 1/2 g. So, and then putting that in terms of pi's and a's, this is plus minus n pi over a. So what this equation says is there's sort of special values of k that correspond to 0, pi over a, 2 pi over a, 3 pi over a, 4 pi over a, and also in the negative direction, where electrons will be Bragg reflected if they happen to have that k. So Bragg reflection means that the electrons are moving in this direction with some value of k, and then we're in 1D, so they get reflected. So they're just moving in the opposite direction with equal and opposite values of k. And if you have two plane waves of the same wavelength moving in opposite directions, you add them together, you get a standing wave. And you can see that when this band gap opens up, you get sort of right at these special values of k, you get a horizontal tangent, which is equal to 0 group velocity. Okay, so that was the messy derivation. And let me show you sort of a neater slide of how to visualize this. So the graph that I drew previously on that slide, it is most similar to this one right here on the right. And you can see that here it's drawn such that there is the same thing present in every Brillouin zone. So this is called the repeating zone scheme. And the way this graph is constructed is exactly what I didn't draw very well on the previous slide. So you start off with with your simple free electron parabola. You introduce the Brillouin zone boundaries, and then you're allowed to translate your free electron energy versus momentum by reciprocal lattice vectors. So they only have two examples drawn here, two translations by plus 2 pi over a and minus 2 pi over a. And then whenever you have bands crossing, you open up a gap. And that is what is shown in the gray images. Okay, so this is the repeating zone scheme. Another way that one can write this information is just translate everything back into the first Brillouin zone. So this is called the reduced zone scheme, and it's in the middle. So going from the repeating zone scheme to the reduced zone scheme, you basically start off with the repeating zone scheme, and every point that is outside the first Brillouin zone. So first Brillouin zone is between pi over a and minus pi over a. Everything outside there, you just translate by some integer multiple of 2 pi over a to get it into the first Brillouin zone. And that is what you end up in the middle. That's the reduced zone scheme. And finally, there is the extended zone scheme, which is on the left. And the extended zone scheme shows different information in every Brillouin zone. So basically, the first Brillouin zone shows the lowest energy band. The second Brillouin zone, which is between pi over a and 2 pi over a and minus 2 pi over a and minus pi over a, that shows the next energy band. Then the third Brillouin zone shows the next energy band, and so on and so forth if we were to repeat this graph until infinity. So let me introduce a little bit of notation. It's going to be important later on. So, I mentioned that there's a gap that opens up at the Brillouin zone boundaries, or wherever you have sort of bands crossing. And a band gap represents forbidden states. So electrons can have energy versus K along the dark solid lines that are here, but they cannot have energy versus K inside the band gap. So the band gap is sort of a forbidden energy that electrons cannot have. The next concept I want to introduce that I probably dropped already several times is the concept of a band. So a band is sort of a continuous portion of the energy versus K. Okay, so this is band 1, this is band 2, this is band 3, and so on and so forth. So band is sometimes used interchangeably with energy versus K. It's just a continuous set of energy and K coordinates that an electron can take on. I think that is all of the terminology that I wanted to introduce with regards to this slide. So we'll come back to these concepts at different points in the remainder of the lecture. So let's see, let me, all right. So, okay. So at this point, I want to introduce a concept that is probably the most important concept in solid state physics. However, in the context of the rest of the lecture, I'm not going to be using it very much, but I just want you to really remember this terminology and remember that it is extremely fundamental. So so basically, the wave functions that describe electrons in a crystalline solid are they take on the form of what are called block waves, and a block wave is defined in the following way. Okay, so the permissible wave functions are written in this way, where so let me just write it. So u sub k of r times e to the I k r. Whoops, let me write this e to the I k dot r. All right, so the second component is one that you've seen already. This is a plane wave. And this is, and the function that multiplies this is some function that has the periodicity of the lattice. So what that means is that if you have some translation vector of the lattice, so some vector that brings you to an identical point in the crystal lattice, and you can apply it over and over to get you to identical points, then u sub k of r plus this translation vector is just equal to u sub k of r. So this function is invariant under translation by a direct lattice vector. When you have a crystalline solid, which is sort of electrons plus the lattice, then the solutions to the Schrodinger equation in that scenario will take on the form of block functions. Okay, so that's all that I will say about block functions, but I want you to really remember that this is one of the most fundamental things in solid state physics. Okay, so I want to, at this point, actually not completely leave block functions, but I want to say a little bit about K. So earlier I talked about K, and I described it as either a wave number or a momentum. And from here on out, now that we have the concept of we are sort of dealing with a minimum viable model of a real solid state system. So we have electrons and we have the atomic lattice. From here on out, it will generally be correct to call this a crystal momentum. So every block function is labeled by a crystal momentum, and um, uh, and let me discuss some of the implications of, or some attributes and implications of the crystal momentum. Okay, so um, so all right. So the first two things that I'll say are kind of mathematical things. The next two things I'll say are physical interpretations. Okay. So one attribute of the crystal momentum is that e to the I k dot t, where t is a translation vector of the lattice, is the phase factor that multiplies a block function when we make a translation by a lattice vector t. Okay, so this is a statement that might be a little bit obvious from the expression for the block function, but basically, let's say you have a one-dimensional lattice. I'll draw a portion of it here, and you have written the wave function, and you know what the wave function is at this point right here, which I'll call R. And then you want to know what is the wave function right over here at this point over here. So this is going to be psi sub k of r plus t, where I'll just call this translation by 1, 2, 3 lattice points. I'll call that t. And then this is going to be equal to psi k of r times e to the I k dot t. Okay, so that is one attribute. Another attribute is if the lattice potential vanishes. So if we turn off the lattice, then we're just left with plane waves. And that is actually precisely where we started. So we started with no lattice, and our solutions to the Schrodinger equation, the wave functions, were of the form of plane waves. Okay, so then let's get into actually useful interpretation. So crystal momentum, it has the word momentum in it. So it is similar to momentum in some ways. So the way that it is similar, I should say it's similar to regular momentum. So I'll write that it enters conservation laws like a momentum. So let's say you have an electron that has momentum h bar k, and it collides with a phonon, a quantum of lattice vibration that has momentum h bar q. Then after this collision, the momentum is conserved. So uh, uh, So, so if that is the total momentum that the two particles in question had originally, then after the collision, then whatever that momentum is going to go somewhere. It might all go to the electron. It might go to some actors that have not been mentioned yet, but this momentum has been conserved. So I'm going to erase this because it's sort of a funny looking equation. And so that's how crystal momentum is like regular momentum. So it enters conservation laws. But it is different from regular momentum in that it is defined only modulo a reciprocal lattice vector G. So let me write that. Okay, so this is a little bit different from regular momentum. And what this means, I think it's easiest to show in the previous slide. So basically, if I am talking about, am I still writing in green? I'm not. Let's write in some color. Okay. So if I'm talking about an electron that is at this K, which happens to be in the third Brillouin zone, then that is exactly identical to if I translated it into the first Brillouin zone by translation vector 2 pi over A, or if I translated it into the second Brillouin zone via translation vector via another 2 pi over A, so 4 pi over A in total. So that is to say that this momentum is not defined only modulo a reciprocal lattice vector. So it's sort of periodic in along this k-axis where the periodicity is set by the reciprocal lattice vector. So that is to say, if I wanted to define everything in the first Brillouin zone, I could just translate everything in the first Brillouin zone. That is the reduced zone scheme. If I started with the reduced zone scheme and for whatever reason wanted to talk about something in another Brillouin zone, it would be equivalent to translate what's happening here by 2 pi over A, 4 pi over A, 6 pi over A, and so on and so forth. Okay, so um, all right. So at this point, I want to discuss a little bit the some of the distinctions between metals, semiconductors, and insulators. I'll also say a couple of words about semi-metals as well at this point. So, all right. So let me begin, I guess, with insulators and semiconductors. So insulators and semiconductors are defined by having the Fermi energy if you are at zero temperature, or the chemical potential if you're at finite temperature. They are defined by having them be inside the band gap. So the picture that you have in that case is that you have a band that is below the Fermi energy that is completely full. And then you have a band that is above the Fermi energy that is completely empty. So if you have an electron that is in an occupied state and it wants to go into an unoccupied state, it needs to traverse the entire band gap. So that is an attribute of both semiconductors and insulators. So for many intents and purposes, semiconductors and insulators are actually the same. So they are defined by having the chemical potential inside the band gap. However, the one difference that they do have is that insulators typically have a larger band gap. Oftentimes, so the dividing line between what is a large enough band gap is that it's higher than optical frequencies. So for that reason, many insulators, so such as window glass, diamond, they are transparent because their band gap is larger than the frequency of visible light. So semiconductors typically have a band gap that is smaller than visible light. So, for example, silicon, which is the most commonly utilized semiconductor, it has a band gap of about 1.1 electron volts, which is in the infrared range. As I mentioned, semiconductor and insulator, from the standpoint of a physicist, they are pretty much the same thing. And in research context, you'll often hear the terminology interchanged. So, as an example of that, one of the materials that my group studies. They are called topological insulators. However, their band gap is about zero point 0.3 electron volts. So it's not just infrared; it is pretty far in the infrared, but it's still called topological insulator because insulator and semiconductor are the same thing to a physicist, and b, it's just what the nomenclature ended up being, and it's stuck. So anyway, semiconductor and insulator, pretty much the same thing, distinguished by the size of their band gap. So a metal, on the other hand, it is distinguished by having the Fermi energy inside a band. So the sketch here sort of shows a scenario not at zero temperature, but at finite temperature. But basically, the idea here is that in a metal, you have your occupied states, but then there are some unoccupied states right above that. So there are low energy excitations that can be made. You don't need to traverse the entire band gap. It should be noted that in a metal, as this drawing indicates, there are band gaps present. However, those band gaps are not sort of relevant to low energy excitations near the Fermi energy because they're located well away from the Fermi energy. So this chart also shows semimetals as sort of an in-between situation between semiconductors and metals. And this is true. And I should say that the concept of a semi-metal, or the strict definition of a semi-metal, is not very well defined. So let's see. All right, let me draw on the previous slide actually. Okay, so for a semi-metal, there are kind of different scenarios where you can get a semi-metal. So one way that you can get it is if you have sort of two bands that sort of overlap a little bit, and then the Fermi energy, sorry, I'm drawing it a little bit tilted, the Fermi energy just happens to cut through both. Okay, so that is, and I'll shade in the occupied states. Okay, so the Fermi energy is cutting through both of these overlapping bands. So that's one way that you can have a semi-metal. Another way that you can have a semi-metal is if you have bands that just barely touch. So there's technically a zero band gap. And then here's the Fermi energy in horizontal. And then you have your occupied states and your unoccupied states just above it. So technically, you can make zero energy excitations from the occupied to the unoccupied, but again, it's sort of on the cusp of being a metal versus a semiconductor. So TLDR, a semi-metal is a concept that is a little bit poorly defined, but generally it is kind of at the cusp of being either a metal or a semiconductor, one way or another. So I should mention a little bit of terminology I forgot to mention on this slide. And this terminology is the following. So the band right below the Fermi energy in a semiconductor or an insulator, that is called a valence band. And then the band right above the Fermi energy is called the conduction band. Okay, and then the band gap is the forbidden energy range that is between the valence and the conduction band, and the Fermi energy is inside the band gap for an insulator or a semiconductor. Okay, so we are approaching uh, uh, a new topic now. Sorry, this mini lecture is not quite done yet, but so I want to now introduce the lattice onto the free electron gas in 2 dimensions because it's easier to draw than 3 dimensions, but less obvious than 1 dimensions. Okay, so for constructing Brillouin zones, that is something that that I teach when I teach solid state physics, but it's not something that I'm going to teach here because this is intended to be a very introductory introduction, and B, one typically looks up Brillouin zones. So here is an example for a square lattice showing several Brillouin zones, so 1, 2, and 3. You will notice that Brillouin zone 1 is continuous, but then 2 and 3 are not continuous. So 2 and 3 are disjointed, and when you get into higher Brillouin zones than this, it gets even crazier looking. All right. So another thing to note is that all of the Brillouin zones have the same area. So if you count the area that is enclosed by all of the triangles labeled 2 and put it together, you'll notice that it's the same as the square labeled 1. And if you do the same exercise for the triangles labeled 3, you'll see that it's also the same as the square labeled 1. Another attribute of this construction of Brillouin zones is that you can translate all of the higher Brillouin zones back into the first Brillouin zones using reciprocal lattice vectors. So I should mention that the dots on this graph represent reciprocal lattice points. So for example, the origin here is 0. The one right in the middle is 0. And then the one that is here at the corner of 2 and 3, that has the x coordinate 0, the y coordinate 2 pi over a, and then this one over here that is on the horizontal side, that has coordinate 2 pi over a, 0, 0, and so on and so forth. Okay, so so our starting point for sort of discussing metals and their Fermi surfaces is drawing the Brillouin zones. So this is similar to what was done a little bit ago for 1 dimension, but in 2 dimensions and also 3 dimensions, more interesting things happen. Okay, so the way that we sort of add the lattice to the free electron gas is as follows. And do I have, okay. So I will just describe what is happening here. Okay, so I want you to focus on this view graph right here, so one on the left. So what has been done here is we have a free electron circle, let's call it. So this is basically a free electron gas in 2 dimensions, where instead of a sphere, it's a circle, and the radius of this circle is still called KF. And we have superimposed this circle onto the Brillouin zones. So you can see Brillouin zone 1 as the square in the middle, Brillouin zone 2 as the disjointed big triangles, and Brillouin zone 3 as the disjointed littler triangles. Okay, so now what we do after this is we examine what is in each individual Brillouin zone. So Brillouin zone 1 is completely full. So if it's completely full of electrons, it's kind of a dud. So it doesn't contribute to anything. The reason is that if we consider the repeating zone scheme, we would just have Brillouin zone 1, this square tiling all of space. So you would have occupied states towards infinity and no unoccupied states. So as a reminder, where action happens is where you have a boundary between occupied and unoccupied states. Okay, so now the second Brillouin zone. So the way that is constructed is you sort of translate each of the second Brillouin zones, each of those triangles, into the uh, into the first Brillouin zone. So basically, you put the one of the triangles like this, another triangle like that, another triangle like that. And you can see that for this triangle that I translated down here, it is sort of, it has a little arc that goes through its tip, and then below the arc are occupied states. So that is precisely this drawing here. If you put it all together, that is what you get. And then finally, in the third Brillouin zone, if you translate all of those into the first Brillouin zone, you get these little things at the corners. And let me just draw the Brillouin zone boundaries on top of this to make it clear. All right, and you can examine, for example, the one that looks like a triangle like this. So that one is this one right here. And you can see that it is that this one? Yeah, that is. Yeah, um, yeah, that is this one. And you can see that it has sort of a propeller on one of its uh, its its tips. No, actually, no, sorry, I misspoke. This one that I have highlighted right here, that is actually this one right here. Sorry, that's this one right here that has the propeller in this corner. Okay. So, all right. So, all right. So there are a couple of things to notice here. So first of all, in the second zone, the continuous region is sort of formed by an absence of electrons. So again, the gray circle represents where there are electrons. It represents the occupied states, the white, the unoccupied states. But in this case, you have the unoccupied states forming sort of a continuous shape. So this is called a hole-like Fermi surface. So that is one thing that appears naturally when you introduce Brillouin zones, when you introduce the periodicity of the lattice on top of the free electron gas. So you started off with only electron-like carriers, but when you introduce the periodicity of the lattice, you can get hole-like carriers as well. Another thing to note is that this information in the third Brillouin zone, it looks like there is not a continuous shape there, but if you draw it in the repeating zone scheme, which I'll draw a portion of here, so if you draw it in the repeating zone scheme, you just sort of repeat the Brillouin zone over again, and you can see that each of these corner pieces forms part of a propeller shape, which is why I called it a propeller a minute ago. Okay, And also I should note that this circle, it extends into this no man's land, which is actually the fourth Brillouin zone, which is just not shown in this example. Okay, so far what I've shown is you have your free electron gas and you have the periodicity of the lattice, but the lattice potential is still equal to 0. So you need to turn on the lattice potential, and in a real material, the lattice potential will always be on. But the turning on the lattice potential is what actually opens up the gaps at the Brillouin zone boundaries. And in the context of a metal, what it does is it sort of rounds out the sharp corners. And also, when you have the Fermi surface intersecting the Brillouin zone boundary, it will always intersect it perpendicular. Um, okay, let's see. What do I have? I have a few more things to. Uh, uh, what else do I want to say about this? So anyway, what I've just illustrated here is essentially what you have is you start off with sort of your free electron gas, and from that you know, okay, each atom contributes this number of electrons. However, once you have information about the periodicity of the lattice and also the Brillouin zones, the actual contributors to conduction, for example, might not be the full number of carriers that went in. So basically, the area, or if we translate to volume in 3 dimensions, the areas or volumes of these enclosed regions, this gives you the density of the charge carriers. So your starting point, this big circle, in the absence of the lattice, that is sort of how many carriers you thought you had. So that's how many electrons per each atom. And then these actual Fermi surfaces, these actual contours of constant energy, where that constant energy is the Fermi energy, those end up being a different area, and they can also be different sign of carriers as well. So this is an example. This illustrates how you can get hole-like carriers, how you get sort of a small carrier density when you thought you put in a large carrier density, just starting off with a free electron model and then introducing the lattice and making it into a nearly free electron model. So this nearly free electron model is a pretty good description of many of the metals on the periodic table, and it should be taken as sort of the default starting point of what is normal behavior. So it might seem weird to you guys as at this point, but sort of in research context, people sort of talk about things that are sort of normal and textbook, and that is this slide right here. And then there are scenarios that are anomalous that differ from this. So this is sort of a normal textbook scenario of what happens in a metal. So basically, just to summarize again, you have a certain number of valence electrons that go into the free electron model. You turn on the lattice and the Brillouin zones, and the actual carriers that can contribute to conductivity might end up being different from what you put in terms of their abundance and in terms of their sign. Okay, so with that, I am going to switch gears one last time, and I am going to talk about um, uh, the tight binding model, whoops. All right, so the tight binding model is another approach for energy versus K relations that electrons in a solid obey. So what we've been doing so far, if we've been starting out with a completely delocalized picture. So our starting assumption is that the electrons are completely delocalized over the entire crystalline solid. So we treat them more like waves as opposed to particles. So a tight binding model is exactly the opposite approach. So you assume that electrons are pretty much localized. So as the name implies, electrons are mostly tightly bound to their host atom. However, they can make small incursions to their neighbor or to their next nearest neighbor or to their next nearest neighbor, however many terms you want to include. And um, and uh, that is the tight binding model. So as the name implies, electrons are tightly bound, but they can make small incursions elsewhere. Okay, so for the tight binding model, so I'm going to give just a very quick derivation, and then the end result is that energy versus K is going to be sines and cosines as opposed to parabolas. Okay, so our starting point is we're going to assume that the wave function that describes an electron in a crystal is given by the following. So n to the minus 1/2, n is again the number of total electrons, and it's a normalization factor. And then we have a sum over j, where j represents each of the lattice sites. And then you have a plane wave e to the I k dot rj, where rj is the position of each of the atoms in the crystal. And then you have some function phi of r minus rj, where phi is a wave function of an isolated atom. So it's assumed that this wave function of an isolated atom is still holds when you have a crystal of these atoms. Okay, so the first order energy is found in the following way. It is found from the diagonal matrix elements of the Hamiltonian. And what is the Hamiltonian? It turns out it won't actually matter what the Hamiltonian is. We're just going to replace it with some number that has units of energy at the end of the day. But basically, what the Hamiltonian is it's going to be describing the kinetic and potential energy that an electron feels in a crystal solid. So anyway, that is going to be equal to n to the minus 1. Then we're going to have two sums because we have a k here and a k here. So we're going to have a sum over j, another sum over an index m, e to the I k rj minus rm. And then we have another matrix element term, which involves the original single atom wave functions. Okay, and I forgot to mention that phi sub m is defined as the wave function of an atom located at position r minus r sub m. So we're going to define a new variable now called rho. So rho sub m is equal to rm minus rj. So basically, it's the difference in position between position j and position m. And then we're going to write our energy in the following way. So we use this notation just to get rid of one of the sums. We're going to write it as a sum over m. Oops. E to the I k dot rho m. And then we have some integral over volume of, and this is just expressing this matrix element. So we're going to integrate over volume, complex conjugate of phi r minus rho m h phi of r. Okay, so this equation at this point, it doesn't specifically use the tight binding aspect. But now we're about to bring in the tight binding aspect. So how that comes in is that we are going to neglect all the terms except those on the same atom uh, Okay, so we're going to neglect all terms except those that are on the same atom. So essentially, rho is equal to 0. So this is called an on-site energy. And also, we are going to leave the terms that uh, that are between nearest neighbors. And this is called a hopping term, because it reflects that we allow an electron to hop from its original site to its closest neighbor and then come back. Um, so, so this is just a choice that these are the only two terms that we're going to keep. We could have chosen to keep the next nearest neighbor term as well, so electrons can hop to the closest neighbor, or they can hop to the second closest neighbor. That is a choice that we could have made. We did not make it here just because I want to keep things very mathematically simple to express this. Okay, so this is the tight binding part. So basically, electron can stay where it is. It can go to its neighbor. So it's tightly bound to its original site. All right, so we're not going to actually solve this integral. So that's why we don't care what the Hamiltonian is. We're just going to give it a number. So we're going to, for the on-site, let me call that 1 and the other one 2. So 1, we have an integral over volume, phi star of r, h phi of r, and we call this negative alpha. So I should mention that in the context of uh, of real physics literature, usually the this is not the nomenclature that is used. And I'll mention what the used nomenclature is in a little bit. Okay, and then the hopping term, so that is psi star r minus rho, where rho is only nearest neighbors, h phi of r, we call this negative gamma. Okay, so alpha and gamma, they are just numbers that have units of energy. They can be determined by assuming some specific form of the single atom wave function phi. However, in practice, what typically happens is that one determines these empirically one way or another. So maybe one does some experiments from which they can ascertain energy versus K. And then from that, they see what values of alpha and gamma, in this case, best parameterize what we just measured. Another way that this can happen is that maybe people calculate energy versus K using more sophisticated first principles methods rather than this approximation. But then for other applications, they want some sort of simple parameterization of what they've calculated. And then they might see what values of alpha and gamma best fit their calculated energy versus K. So alpha and gamma, they are typically determined empirically with the best fit either to data or to a more sophisticated calculation. Okay, so let me summarize what we have thus far. So we have that energy as a function of K is equal to negative alpha minus gamma times a sum over nearest neighbors, e to the I K dot rho m, and that is what we have. Okay, so typically the way that this is written in the literature is the first term is some chemical potential term. It is basically used to set the chemical potential to match the number of charge carriers that are there. And then this term over here is a hopping term, and it usually has the letter T describing it. Okay, so this equation is generally true if you just have nearest neighbor hopping. However, you need some information about the crystal structure if you want to go further. And let's consider a simple cubic crystal structure. So that is just you have you have an atom on every point on a cube, repeating towards infinity in 3 dimensions. So in a simple cubic crystal structure, if you put an atom at the origin, then the nearest neighbors, I'll call that NN for nearest neighbors, they have the following coordinates. So there are going to be 6 nearest neighbors in total in a simple cubic lattice, and they will be located distance plus minus a in the x direction, plus minus a in the y direction, and plus minus a in the z direction. So these are the 6 nearest neighbors in a simple cubic lattice. And then if we just plug in these values of rho, and then for k, we plug in kx, ky, and kz. So we plug, so we're going to have 6 terms in a sum. And it turns out that this sum can be simplified, and we end up for a simple cubic lattice, we get that energy as a function of k is equal to negative alpha minus 2 gamma. So still using the alpha and gamma nomenclature, times cosine kxa plus cosine kya plus cosine kza. And you can see where this comes from. For example, if we just do the x terms, we get e to the I kxa plus e to the minus I kxa is equal to 2 cosine kxa, and same thing for y and z. Okay, so importantly, the energy versus k, they are not quadratic, they are cosines. They can also be sines. So in some limits, so for example, if you consider this near the origin, near kx, ky, and kz equal to 0, it'll look sort of parabolic if you take the first, if you take up to the second order term in a Taylor expansion. But in general, you will have cosines and also sines. So for example, the effective mass here, it will be different at every value of k, because you don't have the simplification that you have in a parabolic energy versus k, where the k dependence just drops out. So that's kind of one example where it's clear that the effective mass will be a function of k. Let me show what this looks like. So this is the function that I just had on the previous slide. And this 3-dimensional object represents the boundary of the Fermi surface. So as a reminder, Fermi surface, I'll call that Fs. It is a structure that exists in K space, and it represents a contour of constant energy, where that constant energy is the Fermi energy. And it separates occupied from unoccupied states. So this is, again, returning back to the fundamental, very important aspect of solid state physics, that a lot of the action happens at the Fermi energy, and an equivalent statement to that is a lot of the action happens at the Fermi surface. So this is the Fermi surface that arises from the tight binding model with only nearest neighbor hopping in a simple cubic lattice. So I think I'll go ahead and end here, but in the notes I have examples for what you get for a body-centered cubic and a face-centered cubic lattice. It's also a bunch of cosines, but yeah, so the tight binding model is something that is really used a lot in contemporary literature, although, as I mentioned, it's usually used sort of as an empirical fitting to either data or calculations. Okay, so that is an overview of electrons in crystals. And much of what I talked about today can be measured in one of the techniques done in my group called angle resolved photoemission spectroscopy, which will be the topic of a later lecture.